Welcome to today's episode of the Data Science Mentor session. My name is Pablo. I am the founder, host, and convener of the Data Science Mentor program, accelerated learning, where folks learn data science from scratch all the way to machine learning, introduction to machine learning. So welcome. In today's session, we're going to be looking at unsupervised machine learning techniques. We're going to be looking at very simple examples. Now, it's important to state that these examples are meant to mimic the, how do I put it? It's meant to illustrate the scikit-learn principles, the estimator API principles, right? But there's going to be a deep dive into these techniques, but it's ideal for us to look at it and then make a sense of it at this point. So we're going to be looking at unsupervised learning examples, right? So let's get started. Now, it's important to state that previously we looked at a simple regression technique, again trying to illustrate estimator API, scikit-learn estimator API guiding principles. We also looked at a classification task, again, to guide us through estimator APIs and their guiding principle, which is basically choose a model, instantiate a model, build a model, transform them, predict, and then you can check your accuracy. But that's different when you're doing an unsupervised learning example. And now we're going to look at an unsupervised learning example, which is known as dimensionality reduction. That's what we're going to look at. Now, again, we're going to also use our flower data sets just to illustrate this really simple stuff, right? We're going to look at it. Now, regression. A lot of activities in the world happen, with a regression technique, with a regression technique, like say if you have fuel price going up and maybe transportation price going up, see some activities like that. So you need to model your data to that assumption and then build a model to it. So which makes it easy for a model to predict. It makes it easy when the model needs to predict a new data, and if it's following that sort of like trend. And then, of course, you need to predict classes in the model. So if we're going to predict fuel prices, we want to predict if it's too expensive, it is cheap, it is average, and stuff. So these are classes. But it's not all the time that you are typically going to predict with labels. Sometimes it's the dimensionality of the data, right? It's the thing. So reducing the dimensionality of the data so that you can visualize it, so that you could, gain insight. So that's what dimensionality reduction is generally. So that's what sort of like the intuition. So again, I'll put that down. It is reducing the dimensionality of a data to gain insights. And one really interesting aspect of it is that it's for you to visualize it, right? Because visualizing is such a huge aspect of dimensionality reduction, right? And so the task of dimensionality reduction hovers around determining whether there is a suitable low dimensional representation of the data you have. Think of it in many ways, right? It's like you have a basket full of tomatoes. Think of it that way. basket full of tomatoes. What can you tell about a basket full of tomatoes? You can basically say it's just a basket full of tomatoes. But sometimes when you break down, when you reduce its dimensions, when you reduce some part of it, you can get to see, oh, well, there's some part of it that's bad. You know what they do when you go to the market to buy tomatoes? If you're living in Nigeria, you go to buy tomatoes. I don't know if it happens in every other part of the world. You see that the tomatoes on top, they're always very beautiful. There's a way these guys arrange it that you look at the tomatoes on top and say, this is what I want. And then they have this way, they just use the polythene, cover it, and now hide the rest of the bad tomatoes inside and then give you. You see, when you don't get back home, you start realizing, you start sniffing, like you want to cry and claim it's onions. But the thing is, reducing data to a lower dimension, right? And still ensuring it retains its essential features also gives us insight. Excuse me. Right. So most times, and most often, dimensionality reduction helps. It has another thing it does. It helps visualize data intuitively. Yep. It can help us visualize data. So which means a lot of the time you could use dimensionality reduction techniques to visualize your data. Even if you're building, say, a supervised machine learning technique, you can also use it as a way of performing exploratory data analysis. Right. Now, but again, this is just an introduction. But the objective of this session is to understand the guiding principles for using scikit-learn estimator API when using an unsupervised machine learning technique. So what we're going to be using today, the technique we're going to be using today is called, excuse me, it's called principal component analysis. It's called the PCA. Again, this is not a deep dive. This is just an introduction, right? We're going to be doing a deep dive later on, right? Let me even make it, let me call it the principal component analysis. Principal component analysis. And that's what it's components. That's what it is, component analysis. Right, so this is what it is. So let me just make it full blown here. Now we're going to use this technique, right? Now it also has it just like linear regression, it also has this linear assumption with respect to dimensionality, with respect to this reducing dimensionality, right? So what we're going to talk about its linear and non-linear reduction techniques later on when we're doing a deep dive. But now, what I want to do is to outline the steps we will typically use when, the steps we'll follow when using estimator APIs for scikit-learn. Now, our first step, which is to choose the model. Now, the steps are almost always different. They are different because something different happens when you're using unsupervised machine learning technique. You're not actually predicting at this point. No, you're transforming the data. So the first thing we're going to do is to choose the model class. So that's the first. Choose model class. Now to choose the model class, we're going to say from sklearn.decomposition, right? Import PCA. That's what it is. That's the first thing we do. Right. So when we run this, we have done our first step. Now, by the way, right? I didn't do, I feel like I didn't do justice. So I have to share the data we're using. So we are using, I think this is it, iris data, irisdata.head. So just this is our data of interest. It's the data of interest. Now, if you're wondering how we did this, please check out if you're in the data science mentorship program, you should see that we have this is 5. So check out 4 when we did simple linear regression and simple classification tasks. And you see that we use the Seaborn repository to bring in this iris data. So this is called our data of interest. So that's what we're going to be working with. Now, again, just so you know, we've broken down this data into we've broken it down into X iris and Y iris. Now we had to do this breaking down earlier on because we wanted to, you know, here we're looking at it in terms of the feature matrix and the target vector, but that's not what we're doing. So we're going to be using the X iris. So this should be X underscore. We have X underscore iris. Oh, let me see. Oh, hold on a bit. What is that? Oh, I think it's a capitalized X. Exactly, capitalized X. So X underscore iris. All right. So with this, it's like we have this, but there's no label. You can see that we don't have any label over here. So that's not what we're working with, right? And you can see that label is over here because we're not label sensitive at this point, right? So that's the thing. So we've gotten our data, right? So we've gotten the first thing, we've chosen our model class. Now the next step we're going to do is to instantiate the model, right? So when you're instantiating the model, it's like you're getting your model started. And when you get your model started, you get it started with some sensible defaults. Yes. So second thing we're going to do is to the first thing the second thing we're going to do is to instantiate a model. So here we can instantiate the model. So here we chose the model. Here we instantiate the model. To instantiate the model, we just simply call it model. And I mean, it's intuitive, really simple stuff. Here we'll call PCA. Please go ahead. Okay, Grace, someone asks, at what point did you expunge the PCA model? So now in our last session, let me just scroll back up here. You can see that when we are talking about the supervised machine learning technique and using scikit-learn estimator APIs, there we must understand that to use the scikit-learn estimator API or scikit-learn API, there is data representation is important. So the first part of it is to have it as a feature matrix where you have not n numbers of n samples and then n features, which is the records and the number of columns. And here you now have the target vector, which is just your labels. Now it's important to that end that if we are now going to train our model in this end, it's ideal that we now have just the feature matrix, which will be feature matrix are either NumPy arrays or pandas data frame, which is this. So then we remove the species. Then we now have our target vector, which is what we now have over here. And so the target vector will now just be this, sample, just that sample. So that's what we have it. So I'm taking this from here, and that's where we're working with. what we're working. So just check out our fourth session and you see it over there. So that's where it is. It's from the last session. Yeah. Now, so PCA. Now, if I was to use PCA, PCA has some sensible defaults, right? That we're going to use. So you can see that it has n components. All these things have stuff, right? You can see here it says the linear dimensionality reduction using singular value decomposition of data to project it to a lower dimensional space, right? And so you can see it has n components, right? So you can see at the n component by default, we basically look at maybe at minimum the n samples and n features, right? And we can choose to, right? Basically, here it says if 0 is less than n components or less than 1, and there's something called the SVD solver. We'll be talking about that. And then they say select a number of components such as the amount of variance that needs to be explained, right? Again, here, this is just like by default what we're going to use, right? So you can see it's basically going to check out its n features, n samples, and n features. This is what we're going to have here. So I'm just going to instantiate this, right? So we've had this here, and I'll instantiate this. So we have this. Now the third thing we're going to do is to fit the model to the data. Again, here 3 fits the model. Fit the model to the data. Again, this is pretty simple. What we just basically do is say model dot fit, right? And then our data is x underscore iris, which is over here. And you see the x underscore iris is this data. So we're fitting this to it. So we'll run this. So you can see that it's set up already. So we fit the model to it. Now, one interesting thing is, remember by default, when you fit the model, it's just going to look at the samples you have. Or also, we can choose to state maybe the dimensions we want to put it to. Say we can choose to say in here, we're going to say n underscore components, right? Let's put it at 2. So let's say we want to bring it down to 2. So you see n underscore components, we're going to bring it down to 2 dimensions because the data we're working with has sepal length, sepal width, petal length, petal width. Is 4 dimensions of this data. Can we have a way we can just make it to 2 dimensions? Okay, so we've done that. Now the fourth part of it is we need to transform, right? This is the part that you would typically not see if you were working with a supervised machine learning technique. So if we come here, let me see if I can scroll up a bit and see them over here, where here we are. So here you choose a model, you choose the model parameters, you get the feature matrix and the target vector, fit the model to our data, then apply the model to new data. That's what we do. But here we have to, instead of applying to new data, we'll transform it. That's what we're doing here. So we transform it after we've done that. So we fit the model. So next thing is we transform the data. So we have to transform it because we're not predicting anymore. So we have to transform from one dimension to another dimension. So we transform the data. Here, again, transforming the data into a second 2 dimensions. We're going to call this iris underscore 2D. That's what we're going to call it. So we call this iris underscore 2D, right? And to say iris underscore 2D, we say model dot transform, right? And then what we do is we take our x, which is that we have our iris data, we take our x iris. and then we transform. We've done that really fast, right? Now, remember I said it from the beginning that when you're using the intuition behind this is to visualize your model, just to see, get some new insights from it. But the objective is for us to look at these four things we need to do when using unsupervised machine learning techniques. Now, to this end, we have our data. So what we are going to do is we already have our iris data, which is this, right? We have our iris data. Now we're going to throw in the iris data as is, and inside of it, right, we are going to create, we're going to create a, a new column. The new column, we're going to call it PCA1. And when we call it PCA1, it is going to have iris 2D, and then we're going to take the first dimension from the iris 2D by slicing it and saying, let's get the first dimension. Then we'll come over here and say iris data, and we'll call the new column here is going to be PCA2, and then we're going to now take iris 2D, which is our transformed model, and we're going to slice and take the second dimension. So we've sliced and we've taken the second dimension. So with this, I'll run this here. And then just because I want, just for the fun of it, just for us to see what we have here, you can see this is our new dimension. Hold on a bit. This is our new dimension over here. I'm trying to make use of my annotator. Excuse me, guys. Sorry for this small interruption. Aha, let me bring back the annotator. So, well, this is what we're going to be checking out. Right. Now, for us to see what we are going to visualize, we need to we need to plot it, right? Now remember, the PCA algorithm has no knowledge of the species labels because it doesn't look, its dimension is looking at, right? So it's relatively going to like create break down the dimensions because it's just going to try to make sense of this dimension. Now to do that, we're going to visualize our data. We're just going to use a Seaborn plot. We're going to use one of the Seaborn plots. Where is the Seaborn plot we're going to use? I think we want to see some relational plots. Yes, we're going to use, is that what we're going to use? Is there a relational plot? Yes, okay, we're going to use a regression plot. Right, we can plot data. Yeah, we're going to use this. So this one, it combines reg plot and facet grid. It is intended as a convenient interface to fit regression models across conditional subsets of data. But instead, what we're going to do is we are just going to look at the two scaled, the two dimensions we have. We're not trying to fit it. We just want to see our dimension. And then we are going to ensure that the fit regression parameter is false. So here, we come back here. So I'm going to visualize our new dimension and see what PCA did. So let's visualize our new dimension. Now to do this, I'm going to use SMS dot SNS dot That's what it is. Now, the first thing I want to do is I'm going to take X. I'm going to be using X, and it's going to be this guy. This is what's going to be PCA1. So I have PCA1. And then Y-axis is going to be PCA2. Then we're going to take our hue. Our hue is going to be the species. So after we check the dimension, we're going to use the hue to break them down into colors and see if it was able to make sense, if it was able to see it regardless of the labels, right? Because we want to see how we broke them down in terms of dimensions, right? So we have hue, and hue is going to be species. Now our data is going to be iris, the iris data here. And then one last thing we're going to do is we're going to look at the fit regression model. We're going to say we don't want to fit it to a regression model, so it's going to be false. Then we'll go on to say plt.show. I should have imported matplotlib plt, matplotlib pyplot as plt. So yeah, look at that. So you can see PCA2 and we can see PCA1 here. And these are the dimensions we broke them into 2 dimensions, 1, and then you can see that this dimension basically just seems to be here. This is the dimension, this dimension on its own is like on its own. And then it was able to look at this dimension over here. So in these 2 dimensions, you can see that it was able to make sense of the different plant species. That's what it is. So so this is what it is. But again, remember that that's not basically what we are trying to do, right? What we are trying to do is to talk about unsupervised learning, a simple unsupervised and learning example. Let me make this a simple unsupervised learning example. So yeah, that's what we have here, right? Again, there's a lot to it. Again, there's another unsupervised learning technique, which is clustering. Okay, let me even use that really quickly. So let's do clustering. We have done dimensionality reduction, right? So we can look at clustering. I feel like we have a little bit of time, right? So let's look at clustering. Now, the clustering algorithm finds distinct group of data without reference to any label. So here, the clustering algorithm finds distinct groups of data without reference to labels. Right, so that's what it is. So now what we're going to use a technique. We're going to use a clustering technique called the Gaussian mixture. Again, that technique, that's not what we're going to look at. Again, what we want to look at is the estimator API principles. So that's what we're going to look at. And I want to make this pretty fast. So remember, first, choose the model. That's the first thing we're going to do. Choose the model. So when you're building this, you always remember these things are pretty important. Choose the model. So we're going to go from sklearn.mixture. We import the Gaussian mixture. Right, so we've picked this up. So let's run this. Now remember, the second one is we have to fit the model. We have to instantiate the model. To instantiate the model is different from fitting the model. So we instantiate instantiate the model. And to instantiate the model, we basically call model. And inside, we're going to call the Gaussian mixture. Yes, the Gaussian mixture. And again, the Gaussian mixture has sensible defaults and has n components, which is by default is 1, and the bunch of things. But by default, we're going to we're just going to look at the n components. We're going to say, let's put it into 3 components, 3 clusters, right? So here, n components, let's say 3. This is the one thing we're going to use, and we're going to run this. Then here, the third principle we're going to use is we're going to fit the model to data. So we'll fit the model to data. Right, as usual, we say model dot fit. Now, and we're going to be using our X iris. Again, remember the X iris does not have anything related to. It doesn't have anything related to the label, right? And then we're going to now say, you know what, let us determine. So now what we're going to do is call the fourth part where we are using clusterings to determine if it has labeled. So what it does is it's going to throw them into clusters, right? So yeah. So what we're going to call this is, what do we call this? The Gaussian model. So let's call this C underscore Gaussian model. That's what we're going to call this, right? Which is like the clusters from the Gaussian model. So we're going to call this. Now, interesting part about this, because we're using dimensionality reduction, when we are now going to, well, by the way, this is, before I forgot, or before I forget, this is the fourth part. And what we're going to do here, we're going to determine the labels. Yep. Because we're not looking at labels, but we're going to cluster them just to look at the clusters and then figure out if they have that, right? So here, we're actually going to predict, because with the cluster, we're going to predict and see if it has clusters. So here, we're going to say model.predict. And then when we come in here, we're going to predict with our data that doesn't have the labeled parts of it, any output. So we're going to use that. So we're going to run this, and it's done that. Now, the interesting part is we are going to do stuff. We are going to visualize this whole stuff again. But before we do that, we're going to now create, go to our data here. We're going to go to our data, which is our iris data. Remember iris data dot head, just to look at the first 2 columns here. We had introduced PCA1 and PCA2, so we're going to introduce cluster here, right? So what we're going to do is we're going to say iris data, and then I'm going to create a new column. That column is going to be called cluster. This is going to be the cluster here. Then our cluster is going to basically be our C underscore GM. So we have this. And so I'm going to now check our data now and say iris data.head. We're going to see our first 5 rows, and we can see that we have clusters here, right? We have several clusters. So we have, there are supposed to be 3 clusters. As a matter of fact, just to make sense of it, I will basically come here, because this is the data here, copy this, and then check the unique features that we have here. So check unique. It's going to tell us how many clusters. We got 3 clusters here. Right now, what we need to do is to visualize these clusters. Again, just like we did before, right? We are going to use the PCA that we had before, and we're going to use the PCA we have from our data, and then now say, you know what, the column we're looking at is in clusters. So now we have two things going on, right? So we're going to say SNS dot X is going to be PCA1. Y is going to be PCA2. Of course, what our interest is the species. So our hue is going to be species. Then we're going to now introduce something called call, because we're going to place this in the columns that we would have, and the columns we're going to be working with is going to be cluster. We introduce a cluster. As usual, we are going to look at fit regression, and we'll make it false. And this is it. And then we'll have plt.show. We'll run this, and let's see. It says missing required data. Oh, you love the data. Interesting. Our data is our iris data. This is our iris data. Because we didn't predict the data, so it could not even reference anything. So here you can now see we have three columns. First column is cluster 0. You can see, right? And the next column here is cluster 1, which is all PCA, right? They're all PCAs here underneath them. And then for the y-axis here, you can see PCA2, right? So we have 2 dimensions, and still with the 2 dimensions, it was able to, create a fair enough cluster. Even though you can see a wee bit of this cluster here over here. You can see some of them got into this place. Right, again, just like this guy over here, we just took one of these guys and now was able to split them into clusters. So yeah, so it's with that, right, it broke them into the clusters, right? So this is basically, again, to round up, what we have going on is using is basically saying, look, if you're using an estimator API, scikit-learn's estimator API, there are principles to using it. At the same time, just to share what a simple unsupervised learning example is, right? Now, in future, you're going to apply this in different problems, right? Say you have houses, you're typically trying to figure out different clusters of houses, and these clusters mean something. Maybe you are looking for cheap houses, affordable houses, expensive houses, houses that are neither affordable nor expensive. Now, maybe the upstream team would have cleaned up the data, right? They would have cleaned up the data. They would have done a bunch of things to the data, and then they'll pass it on to the downstream team that now picks up the data to see if there's anything they can work with it. And if the data now has, if we now have maybe the data is supposedly having clusters of different types of houses, then you can use an unsupervised machine learning technique to split them into clusters or reduce the dimensions and see if there is something that any insights it exposes. Again, unsupervised learning techniques are typically like visual, right? This kind of technique will give experts a clue into relationships, right? So this is it. This is what we have done. So in the last 2 sessions, we have looked at last 3 sessions, simple regression techniques, simple classification technique, and then now we've shown simple unsupervised learning examples. We've looked at them. Now, going from here, the next thing we want to look at is to understand uh, hyperparameters and also what validation techniques. All these things are different steps, right? That help you make sense of the whole ML learning the machine learning ecosystem on ideas. Remember, you're not just writing this code typically just to write it. You're going to be solving real world problems with them. So yeah. Do you have any questions? Do you have any questions? Please feel free to share. If you're watching this session, this recorded session, then feel free to drop a message in the Telegram channel. Hello, Grace.
Good day, sir.
Yeah, right.
Please, I would like you to throw more light on what PCA is all about. I didn't really catch that point.
Okay, so PCA means principal component analysis. It is a technique. It's an unsupervised learning technique, just like you would typically say, like a simple regression learning technique. It is used to scale. It's used to scale the dimension of the data you have, right? And to scale that data to a lower level for a different dimension to see if you can have if you can extract insights. Now, the thing about it is that you can look at it from two perspectives: linear and non-linear PCA. But we're not doing a deep dive into it right at this point. But the reason we're going to be doing this is just to show how you can use the estimator APIs. These are the estimator APIs, how you can use them in case you're building a simple model. You can see that's why there's this whole 1, 2, 3, and 4. But PCA is typically for reducing the different dimensions of your data so that you can find insights to it. It has a lot of assumptions, but this is just basically the intuition for it, right? Just like you can look at the Gaussian choice, part of the idea is to recover underlying labels in data, which is if they're in clusters, it can recover them and show you if without reference to any label. So that's what PCA is basically. But again, we're going to do a deep dive on it, and then we'll think about what the intuitions are and how you can use those intuitions to solve real world problems. Yeah, but for now, just think of yourself as a biologist or somebody who looks into flowers, and your job was to figure out this data you just stumbled in, how can I have them? How can I find any underlying cluster or underlying dimension that shows insights? All right, I think this should be it